This is a new capstone, 1685, design of autonomous vehicles.
There are a bunch of news articles recently about spaceships landing on the moon and then tipping over. And then that's like the end of the mission because you can't reach it, you can't go pick it up.
It's a very hard and difficult engineering problem because once you launch this lander into space, you basically can't communicate with it, you can't control it by hand.
So the class has been centered around creating an autonomous system and having it being able to land safely without our control.
We've given students robots before and given them pieces of missions to execute, but it's very structured and doesn't have a lot of design. In this course, we've given them an overall mission and said, okay, now you figure out what would be the right design.
And the class goes all the way from the mission to the requirements, and then think about requirements, then you think about component software, and then about mid-semester start getting into the implementation of, okay, well, let's start actually building that software stack and start integrating it over the past month or so.
The mission that they're going to fly is they're going to take off on the east side of the high bay, fly over to the west side of the high bay. They'll have some finite amount of time to scan the area and figure out where the best place for them to land is, and then try to land right side up, obviously.
If you're exploring an extraterrestrial body, you might be looking for rocks. There might be 3D structures you got to fly into and fly around and explore.
We have a bunch of objects, the cones and balls, which are the things they're looking for, and we give them a rank ordering of importance. And then all these other boxes are then part of that terrain.
We actually have no idea exactly how the environment is going to be set up for our final challenge. And the goal is for the drone to be able to make those decisions in real time, and that's why we've been doing so much testing.
We have a lot of tools that are available to us in this controlled high bay environment, but we do want to make the missions more close to what would happen if we were actually going to, say, like fly a rover to the moon. So we only focus on what we have available on the drone.
It's got a camera and a LiDAR sensor, and it's recording and pretty much seeing this environment and mapping it.
We, for a while, had our drone really wanting to come in here to explore. It could see through the nets. So we had to write code that was like, hey, can't see past that point, because even if it sees it as like a frontier that it wants it to explore, it's not safe for it to do so.
Part of what makes this a particularly AeroAstro relevant subject is the fact that we really emphasize the systems level thinking. And when you make a design decision or an implementation decision, what are the impacts it's going to have on the whole system?
Once we write up our programs, we test them using either a simulation or unit test cases that we've developed. And then slowly, one by one, we start adding things onto the drone's computer and testing them individually. But we need to make sure they can talk to each other.
So, don't just do things in simulation and expect it to work in real life. So we talk a lot about the sim to real gap. Well, there's experiencing this now.
Being able to see something that you've taken from the very beginning design stages all the way to seeing it work, I mean, that's kind of the dream.
The reality is, for a very hands-on practical course like this, you really need great TAs. Having a TA that can sit with the students for like a couple of hours and like help them really dig into like what's going on with their software and what the limitations are and bring a wealth of experience, that's incredibly important. And these three TAs have been amazing.
But, I mean, the students are the ones doing most of the work, obviously. We're the tech support, for lack of a better term. A lot of it is standing next to them saying, I don't know what's causing that problem, but here's what I would do to try to figure it out. And that's how real jobs work, that is how the real engineering works. There's people with good intuitions about things, but if everybody knew all the answers already, the problem would have been solved.
As a kid, I always thought if I learned enough at school that I would find the math equation that could solve any problem. But realistically, engineers only work essentially with approximations, and we do the best we can with the tools that we have, and we're still able to do incredible things under uncertainty, especially under uncertainty.
Just land on the ground if you can. Okay. Are we at the table?
The final performance is less about are they able to complete the entire mission? That's what we'd like to see. If they don't, that's fine. What we do want to see is robust implementation of the various components.
And it's a hard problem. I mean, this is in no way solved in industry or even in research settings, but we get a lot of satisfaction out of training the students.
And particularly get the satisfaction out of it when you go see what they do next.
Yeah,
right?
That's right.
Because, both Nick and I have trained students who now are the ones that are responsible for landing the SpaceX booster, the Google Wing. So just things like that where you look at it and go, we didn't do that, but we trained the people that went to do that.
We're team slam dunkers.
And that is, as John said, our product is ultimately people. Sometimes, if we're lucky, a little bit of understanding along the way, but it's mostly the people that we generate.
Mostly people.
Yeah.
Flying the mouth of the cave.
Takeoff site.
Receiving the spin on trajectory.